Hello, class. Today's lesson is a continuation on a series of lessons dealing with stoichiometry. Today, we're going to tackle an application of the law of conservation of matter, particularly with balancing chemical equations. We'll also attempt to discuss some more stoichiometry, dealing with gram and mole conversions, and specifically gram to gram conversions. So some things to remember from first year chemistry is that chemical reactions are the results of a chemical change. When this occurs, atoms are reorganized into one or more new arrangements. The way this is done is by breaking bonds of the reactants and by forming new bonds to form new products. Something to recognize is that a bond breaking process always requires or absorbs energy. It takes energy to pull atoms apart and break their current intramolecular interactions in order to rearrange. Once they are free of their current intramolecular interactions, such as covalent bonds or electrostatic attractions, they are able to then form new attractions, which releases energy. And if we are absorbing energy, that process is called endothermic. Energy must go into that system. If it is releasing energy, it is called exothermic. Heat is leaving or exiting the system. So the way I remember those is endo, I think of enter, and exo, I think of exit. Now, these two ideas are somewhat contradictory to what you may have previously learned in a biology course. Specifically, there's a misconception dealing with ATP and the breaking of a phosphate bond, and this idea that breaking that phosphate bond releases energy. Something to recognize is that a chemical reaction is a process from reactants to products. If we're breaking bonds of reactants and forming new bonds with our products, there can be a net release of energy over the course of the reaction. That is looking at the whole system, not looking at the individual process of bond breaking and bond forming. So yes, in the ATP process, if you break the phosphate bond, they generalize and say that energy is released, but what they're really saying is, as a result of breaking that bond, the new things that form release more energy than the energy needed to break that bond, and therefore we experience a net release of energy. But bond breaking itself is still endothermic and always will be endothermic. When we look at a balanced chemical equation, we know that it shows the relative amounts of reactants on the left side and products on the right side. And we use coefficients to represent how many molecules we have engaging in the course of that reaction. The coefficients can also be viewed in terms of moles. So you can look at the coefficients and think mole ratio, or you can think number of molecules. It's relatively synonymous for the applications that we're using it for. The coefficient is that number that we place in front of each atom or molecule, and that's what we use to balance our equations. And of course, as I mentioned earlier, this is necessary because of the law of conservation of matter, which states that energy cannot be, or matter cannot be created or destroyed, and this also goes along with energy. Energy cannot be created or destroyed. They can only be transformed from one type to another. So what that essentially means is that the type of atom present in a chemical reaction and the number of those atoms in that chemical reaction must remain the same from reactants to products. What you'll notice, especially in my example here dealing with ethanol, is that it appears during the course of the reaction we go from 2 carbons in C2H5OH down to 1 carbon in CO2. So we need to use coefficients to balance that out, so that way it appears that there are 2 carbons on each side. And we're going to do that with every single element, and it's kind of a step-by-step process, so we'll take a look at that. After each element or compound in a chemical reaction, state symbols are included. These are necessary to tell us important information, such as whether or not the substance is a solid, liquid, or gas. There's a fourth state symbol that we frequently use called AQ, and that refers to an aqueous solution, meaning you have some sort of compound that is dissolved in water. So let's look at our unbalanced reaction here of C2H5OH. One particular strategy, and we'll see this as we go, is that we should start with the most complicated looking molecule and count up the number of atoms on each side. So let's start with ethanol, C2H5OH. Now this tells me I've got 2 carbons, and I know it says H5, which would mean 5 H's, but that second H after the O tells us we actually have 6 H's, and then we have 1 oxygen. We also get 2 additional oxygens from O2. So in total, we have 3 oxygen atoms on the left. On the right side, it appears we've got 1 carbon, we've got 2 hydrogen, and then we have 2 oxygen from CO2 plus 1 oxygen from water. So we have 3. As you can see, these are not balanced because I have a different number of atoms on each side with the exception of oxygen. So I'm going to go through one atom at a time and place numbers so that way we can multiply and then balance our equation. So for CO2, I'm going to start with C. If I have 2 C's on the left, if I place a 2 as my coefficient here, that multiplies by the subscripts in my chemical formula, and I left with 2 carbons because technically the subscript of carbon in CO2 is 1, and what I've done is I've added another CO2 molecule here. I'll even try and color code for you. By adding another CO2 molecule, I now have added 2 oxygen and 1 carbon atom to my system. I've balanced out the number of carbons. I have 2 carbons on each side, but I've also changed my number of oxygens. And that's something we're going to have to work on and kind of plug and play as we go. So I'll just keep track of my oxygens. I now have 5 oxygens total. And then I'm going to move on to the next element. The next element that's unbalanced is H from my original most complicated molecule of ethanol. I have 6 H's on the left and only 2 H's on the right. So if I want to get to 6 total H's, by placing a 3 in the blank, 3 times 2 H's gives me 6 H's. Now, this also is going to change our number of oxygen. I had 4 oxygen on the left, 4 oxygen from my CO2, and then I only had 1 oxygen from my water. By adding 3 more molecules of H2O, I am adding, I'm going to use just non-filled in circles here, I'm adding 3 hydrogens in total to my system. So if you look at the particle diagram here, I now have 1, 2, 3, 4, 5, 6, 7 oxygens. I'm going to put the number here, 7 oxygens on the right side of my equation and only 3 on the left side. So the way to balance this is by adding more oxygen to the reactant side. So I've already balanced carbon and hydrogen. I want to leave this alone. I don't want to touch my ethanol because I've already balanced that. Now, I have 3 oxygens and I need to add 4 more. If I add 2 more molecules of O2, by adding 2 more molecules, I now appear to have 7 oxygens total, and I am balanced. Since I added 2 more molecules, I have 3 molecules in total, 1, 2, 3. So my coefficient is 3. Notice that the coefficients refer to the number of molecules, not how many that you added. Yes, I added 2 water molecules. Yes, I added 2 oxygen molecules to my current system, but I go with the total number. So since I've got 1 ethanol, 3 oxygen, 2 carbon dioxide, and 3 waters, I have now balanced my system, and I have the same total number of atoms on both sides of the equation. Okay, now that's really important. We can double check our work in a second. I'll scroll down here, and you can see that is exactly what they came up with when they balanced the equation, coefficients of 1, 3, 2, and 3. And I'm glad we worked through that because now we can come up with this list of strategies that will help us. As I stated, start with the most complicated looking molecule. You cannot change the chemical formulas. So the small subscripts after each atom have to stay there. You cannot change those. You can only change the coefficients in front of the atoms. If you get stuck, double the most complicated looking molecule and try to rebalance. And then reduce or simplify coefficients if possible. So for instance, if I have coefficients of 2, 2, 4, and 6, all of those are divisible by 2. So if I divide each of those by 2, I get 1, 1, 2, and 3. Polyatomic ions, which I mentioned you need to memorize in a previous video lesson, make sure you keep those grouped together while balancing. Recognizing when you have a polyatomic ion can certainly help you and save you a lot of time with balancing. As long as it looks the same on each side, then it's easier to count them in groups. And of course, always double check your work. So before we jump into 2 more balancing examples, some common reaction patterns that we'll discuss a little bit more in a later lesson, but will potentially help you when balancing, are these 5 reaction types. Metals and halogens react together to form an ionic compound. M sub A, where that's your metal and A is your subscript for that metal, and X sub B, where X is your halogen and B is your subscript for that halogen. We have hydrocarbons, C sub X, H sub Y, where X and Y are your subscripts, react with oxygen in a combustion reaction. As it burns that hydrocarbon, we form CO2 and water. Metals can oxidize, aka they can rust in the presence of oxygen to form a metal oxide. Metal carbonates can decompose. That carbonate ion can be unstable, and we'll see that with carbonic acid in a minute, but as a result of it being unstable, CO2 can be released by a carbonate as it decomposes. So we form a metal oxide and CO2 by decomposing a metal carbonate such as calcium carbonate. Carbonic acid is very similar, but because we have hydrogen present, we not only get CO2 released, but we get water as well. So carbonic acid will always spontaneously decompose. All right, let's do a couple of balancing equations. I think these ones are a little challenging. Well, the first one's not so challenging, but the second one's challenging. If you can do these 2, then I believe that the You Try It set 10 will be a breeze for you. So it says chromium compounds exhibit a variety of bright colors. When we have solid ammonium dichromate, which is NH4, actually let me change my pen color, NH4 2 Cr2O7. Oops. Oh, where's my pen? There we go. This can decompose when it's ignited. And when it decomposes, it forms chromium 3 oxide, N2, and water vapor. So we want to try and balance this out. This is a solid. It decomposes into solid Cr. It says chromium 3. So this is one of those things, remember back when we did formula writing, you check your charges, and then you do your crisscross. So we get Cr2O3 as a solid, plus nitrogen gas, which is diatomic, so that's N2, and then water vapor. Vapor is a gas, so we get H2O in the gas form. All right. Remember that when you have parentheses, the number outside of the parentheses distributes times the number on the inside of the parentheses. So on the left side of the equation, we have 1 nitrogen on the inside of the parentheses and a 2 on the outside. So we really have 2 nitrogen on the left. And I see 2 nitrogen on the right. So nitrogen is balanced, and we can move on to the next atom. Again, I started with ammonium dichromate because that's the most complicated looking thing, and that's very wise to do. So H, we've got 4 on the inside times 2 on the outside, which means we've got 8 on the left. In order to balance that, I only have 2 hydrogen on the right. So to balance the 2 hydrogen on the right, I need a 4 here. 4 times 2 would give me 8. Now I can move on to the next atom. Chromium, it seems I have 2 of them on the left and 2 of them on the right, so that is balanced. And then with oxygen, I have 7 on the left, and then I have 3 here, plus Now that I've put a 4 in the blank for next to water, 4 times 1 is 4. So I have 3 plus 4, which tells me I have 7 oxygen. Since I have 7 oxygen on both sides, I am now balanced. Now you can either leave it blank or you can put a 1 in the blank. I always recommend just putting a 1 in the blank. And the balance for this reaction is 1, 1, 1, 4. Let's go on and try the next one. Now, spoiler alert, and you'll see as we go through, this is one we may have to double. So let's go through and try it. I see 3 carbons on the left, so I know I need 3 carbons on the right. I see 6 hydrogen on the left, so I need 3 times 2, which is 6. And I end up with my 6 hydrogens on the right. The issue with oxygen, however, is that I've got 3 times 2, which is 6, and 3 times 1, which is 3, which gives us 9 oxygens. And I see an odd number here. 9, the only way I can get to 9 and balance it on this side is by putting a 4.5 in my blank. 4.5 times 2 would get us 9. Now, the issue with this is that coefficients refer to moles, but they also refer to number of molecules. You cannot have half of a molecule. So this is where that doubling comes in. Double the most complicated thing and start over. So I'm going to put a 2 in my blank here. And I'll keep in mind that that is 4.5 at some point. So 2 times 3 is 6, which means this also doubles. And 2 times 6 is 12, which means that also doubles. So I scaled up from 3 and 3 to 6 and 6. And now if I check my new totals, I've got 6 times 2 is 12 oxygen, 6 times 1 is 6 oxygen, and this is 18 oxygen total. 9 times 2 gives me 18, and I have officially balanced 2, 9, 6, and 6. The other way you could have done that is put in all of your coefficients that we had before, even though there's a decimal, and if you multiply all of these by 2, then you would have gotten the same coefficients that we had just gotten. So there are a couple of different strategies for how to do that, okay? All right, let me keep an eye on my time. All right, so go ahead and try the balanced chemical equations below. There are 4 of them here, and quite a few of them you may have to do that doubling thing, so keep that in mind. In our next lesson, we'll briefly talk about our mole ratios and gram to gram problems. I thought we'd have more time in this one, but that is okay. See you in the next one.